Hello, folks. We're going to talk about acid strength and equilibrium today. We'll start with strong and weak acids and bases. So, a strong acid is a strong electrolyte, meaning it conducts electricity. Practically all acids are going to ionize, which means separate to a degree. Same thing with strong bases. They will conduct electricity very strongly. And again, all the base molecules will again break apart and form OH minus ions, either through dissociation or the reaction with water. But then on the other hand, you have weak acids and you have weak bases, okay? And those don't break apart completely, so to speak. Only a small percent will ionize, or if you're a base, dissociate, meaning they conduct electricity very weakly. So if you had a light bulb set up connected to those, they would not light the light bulb up. It would be very dim, okay, just on a little bit because they don't completely break apart. Now, the stronger the acid, the more it's willing to get rid of that hydrogen or donate it, okay? And strong acids, again, practically donate all their hydrogens, okay? And therefore, it's a strong electrolyte. There is a list of strong acids that we would like to know: hydrochloric, hydrobromic, hydroiodic, nitric acid, and then you have H2SO4, sulfuric, and also perchloric acid, okay? And there's the light bulb. Okay, so HCl will light it up. If you have pure H2O, not tap water, it won't light it up. Weak acids, again, only a fraction are going to separate. So actually about less than 1% actually break apart. Okay, so you end up not having a lot of ions in there. So it's just very dimly lit here. Okay, and that'd be hydrofluoric acid solution there. Same thing with bases. Bases are going to accept hydrogens. Okay, strong bases, practically all molecules will break apart, and therefore you are going to get all those OH minuses floating around. Now, weak bases only partially break apart. We call those a weak electrolyte. Most of them will not take the H from water, and much less than 1% again are going to ionize. So again, here's the strong acids: perchloric, hydrochloric, hydrobromic, hydroiodic, nitric, and sulfuric. And then these are the strong bases. So these are the main ones: lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Okay, but these aren't the only acids and bases. Okay, these are 6 strong acids and bases. Okay, now the stronger the acid that you have, the weaker the attraction of the ionizable hydrogen for the rest of the molecule is. Okay, so the stronger the acid, the weaker the conjugate. So here we have HCl, and its conjugate is Cl minus, which is a weak conjugate base. So again, the stronger your acid or base, the weaker its conjugate is going to be. And we talked about water already being amphoteric and all that, and it's actually extremely weak electrolyte. It does not, conduct electricity very well. Only about 1 out of every 10 million water molecules will actually form the ions OH minus and H3O plus. And when it does, it's called autoionization. So here's that H3O plus and OH when 2 waters get together, but it only happens 1 out of every 10 million water molecules. Now, all aqueous solutions contain both H plus and OH because you're in water. So H and OH, water, okay? But the concentrations are equal, right? Because that makes sense. Every molecule breaks going to get 1 H and 1 OH minus, okay? And we can look at that as being equal to each other, being 10 to the negative 7 molar at 25 degrees Celsius. So that'd be the concentration of both the hydroxide and the hydrogen, okay? And that's where we get this ion product of water, which is the Kw, okay? So if you multiply both those, it's 1 times 10 to the negative 14th of water. So H and OH make water, right? So Kw, this is your total. So if I use my Kw and I know one of the concentrations of either the base, the OH, or the H, the acid, you can find or solve for the other one, okay? And as H goes up or increases, the OH minus must decrease. That way they both are going to still multiply to equal the 1 times 10 to the negative 14th. Okay, so they're inversely proportional. As one goes up, the other one goes down. Okay, now neutral, they would have the same. Both would be 1 times 10 to the negative 7th. Acidic solutions have more H plus, okay, and basic solutions have a larger OH minus, okay. Now remember, you're dealing with negatives, so larger would be -6, -5, -4, -3. Those are the bigger numbers. If you're going -8, -9, -10, you're actually getting smaller. Okay, and here's an example with barium hydroxide showing the Kw equal to those two concentrations. And in this problem, they give you a concentration of the OH. Okay, so you can solve for the H. Now, one key here is there's not just one OH, there's actually two. So whatever the concentration is up here, the 0.0002, you want to double that because there are two OHs that are going to ionize and be floating around in solution. All right, so we plug that in. So instead of 0.002, it's 0.004, or you can put it in scientific notation here, 4 times 10 to the negative fourth, same thing. And you just divide, do the division, you get 2.5, 10 to the negative 11th. Okay, here's another problem here, 3 different ones, where they're giving you base concentration, and another base, but this one's double, remember. So you have to take that 0.2 and make it a 0.4. All right, here is the table. As you have more H plus acid concentration, you have less base concentration, and vice versa on this side, less acid, a lot more base. Okay, so remember, here's your acids on this side, a lot more H, and base on this side, a lot more OH. Okay, so even though it may look like it, the H or OH will never be zero. You'll still have a little bit of it. Okay, and that's it.